So let's go ahead, just simply take a look at the review sheet. And I do have a little bit to add to it, just here and there, all right? Does this, yeah. Okay, so this time I kind of took it and I spread it out a little bit, so hopefully I have a little extra room. So the general structure of an atom, of course, what's in the center of an atom? Nucleus, yep. Let's see if I can, draw an atom. So we have the nucleus. Nucleus in the center, and then what's around the nucleus? The electrons. Yep, we have electrons outside the nucleus. Do you guys remember, because this is on your test, do you remember, so what's in the nucleus? What particles are in the nucleus? Electrons and neutrons. Yep, you got it, protons and neutrons. Perfect, protons plus and neutrons is 0. So do you remember which of those electrons, protons, or neutrons actually say what element an atom is? It is the protons. Protons win. Yeah. So actually when it comes time for saying which element it is, actually it's the protons that equals element. Okay, and actually we kind of did some things, kind of looking at the periodic table, that's that whole number. Okay, number of protons equals element. I'll go ahead and say number of protons is equal to the atomic number. Atomic number. That's actually coming up. Okay. All right, the next term there, or the next talks about electrons, how we say electrons can actually be, remember I brought in that light that glue red, okay, and it was a neon, and actually you guys held up little diffraction gratings, you could see lines there, okay, so electrons can be, let's see, how do I say, ground state, excited state, electron. So let's just do it this way. These are energy levels, okay, I'll put E for energy, okay, energy levels right there, and so we said an electron can be here, as far with regard to energy, or it can be up here, more energy. Down here, we call this the ground state. Ground, ST for state. And here we call it an excited state. Okay. And then actually we said that if you zap an electron with energy, it can go from the ground state to an excited state. Okay. So that blue line actually is you add energy. Adding energy, and then actually I'm going to do a red line over here. It's going to go from an excited state down to a ground state, and actually that energy will be released. E, or energy released. And it creates those cool lines like we saw. Okay. Oh gosh, that's these two actually. The next one, neutral atom. Okay, let's start with the first one. And if a neutral atom gains electrons, okay, if it gains electrons, will it be positively or negatively charged? Positive. If it gains electrons. It's going to be negative. Yep. Positive. Neutral atom gaining electrons is going to be, let's see, neutral atom gaining electrons, it's going to be negatively charged. Oops, gosh. Negatively charged. And what do we call a negatively charged thing? An anion, yes. Okay. Well, what about a neutral atom then losing electrons? It's going to be positively or negatively charged? It would be positively charged, yep. Positively charged. Exactly. And then what do we call positively charged thing? Cation. Yep. And one last thing before I leave this. If we're looking for something to form an anion, gain electrons, we talked about how we have metals and nonmetals. Which one tends to gain electrons? What do you think? Yep, she's pointing over here. Yeah, it's the nonmetals tend to gain electrons. Exactly. Okay, so I'll add that too. Nonmetals. Pick a different color. See if this green shows up. Non-metals. So what loses electrons then? The metals. And I'm going to go ahead and, so I'm capturing this video, and I'll push it out under Twitter, and I'm also capturing these annotated sheets, and I'll push those out on Twitter too. Okay, the Heisenberg uncertainty principle, the big thing I want you to know there is it applies to very small things. Okay, so that's kind of the answer. It's a multiple choice question. Applies to small things like electrons. Okay, then on to chapter 10. All right. So atomic number, what's the atomic number, did we say a minute ago? It is the number of protons. Perfect. Equals number of protons. And then what's the mass number?
Protons plus the neutron?
Yes, exactly. Mass number is protons plus neutrons is equal to mass number. Yep. You got it. And then isotopes, do you remember, like if you have carbon has different isotopes, what's different about carbon atoms that are isotopes of each other? Which subatomic particle is different? It's not protons, because they all have, carbon is atomic number 6. They all have 6 protons. It's not electrons. It is the neutrons, exactly. So isotopes differ by the number of neutrons in them. Yep, just differ by number of neutrons. And neutrons is like an N with a little superscript 0 because they're neutral. Yep. And then the next one, number of protons, neutrons, electrons in an atom or ion. So let's just do a quick example. If we pick on calcium over there, so for instance, you could see this. Let's go, and I don't think I did any ions, so actually it's just going to be atoms. So in a neutral calcium atom, and then I also have to give you its mass number. So let's go with the isotope calcium 41. So if I say calcium 41, it's like the examples that we worked in class. That 41, if you find calcium in the periodic table, you're like, well, I know it's not the number of protons because calcium is atomic number 20, right? So that 41 actually is the mass number. Okay, and you guys told me up here that the mass number is the number of protons plus neutrons. So here we go. We could knock out the number, what's the number of protons in every calcium atom? You have a periodic table tomorrow. Did you say 20?
Yeah, that's what you
Yep.
said.
It is 20. You see where that came from? Just from the periodic table. Let's go with electrons. If it's neutral, how many electrons are there?
20.
Also 20. You got it. Okay, and then here we go. Number of neutrons, which kind of can come and go depending upon the isotope. This is the one where you take the mass number, the big number, and from that you subtract the atomic number, the number of protons. So if I take 41, which is protons plus neutrons minus protons, which is 20, I get neutrons. So 41 minus 20 is equal to, I get 21. 21 neutrons. Okay, so that's kind of where that is. 11. Lots of stuff here. So remember, let's see, how do I want to do this? Remember how we've been talking a lot. If you can take matter, and it's like I call it a logic tree, and it's either pure or it's a mixture. And then if it's pure, you have two options. You can have, you could be an element, or it can be a compound. I'll put CPD for compound. And your two options for mixtures are homogeneous, homo, and heterogeneous, hetero. Okay, so that's what this is up here, classification of matter. So, you know, I don't have a lot more to add to that. Be able to recognize, for instance, like if I say water. Water has to be either an element, a compound, or a mixture. How many people think water's a pure substance? Water is a pure substance. Yeah, water is a pure substance. So water actually is an element or a compound. It is a compound. Yep, water. Now, if you had salt water, okay, salt water, how many people think salt water is a pure substance? No. It's a mixture. What if you had salt water that was totally the salt was dissolved? How many people think that would be a homogeneous mixture? Yes, it would be. So that's the kind of question there. Most abundant element in the universe. I went ahead and put this on the test. Anybody know what it is? Remember what it is? It's the simplest. It's the lightest. Hydrogen, exactly. I wanted to include this because actually that's going to be a player in astronomy. There. All right, so periods and groups. Periods go like across, right? So periods go like this, and groups go up and down, right? So elements with similar chemical properties, is it in the same period that they're the same, or is it in the same group that they're the same? Group, very good. That's totally right. So this would be same group. Which I think it's going to be, might be helpful. I can't remember it because it didn't make the review sheet, but we named some of those groups. Remember, and I'm going to have you look up the names if you don't mind, but group 1A, we call those alkali metals. Okay, so I'm going to say 1A. Oops, not Roman numerals. Okay, group 1A, we call those alkali metals. Group 2A, we call those alkaline earth metals. And then we skipped over to 7A. Do you remember what the name of those are? Halogens. Yep, and then 8A, those are our rare gases, or inert gases, noble gases, same thing. So know those names.
What was the gases?
The rare gases are 8A. Yep, they're rare. They have three names, so they're rare gases, inert gases, and noble gases. They're all the same. You got it. And then match the name and the element. So this is like at the last section, and I kind of got 3 and 3. So I'll give you the name of 3 elements, and you have to give me the symbol. And I'll give you the symbol for 3 elements, and you get to give me the name.
Okay.
Yep. Valence electrons, I'm going to put is equal to group number. Okay, so we talked about the whole, 1A, 2A, 7A, and 8A, but actually all of those A's, you just look at the group number, and that's the number of valence electrons there are. Okay, this test the Lewis structures that you guys did, that didn't make it to this test. I just ran out of room. Okay, let's see, common charges for elements. Okay, so that's where, like at the top of your periodic table, or since you guys get a note card, just on your note card somewhere, you might put 1A and +1, okay, because 1A metals form a +1 charge, okay. So I'll just kind of briefly, I'll just remind you. So +1, +2 is 2A, +3 is 3A, okay, and then actually I usually skip. I kind of go backwards from right back to left again from 7A. So 7A, you guys would have put a -1. For the halogens, you would put a -2 next to it. That's what, 6A. And for 5A, you would put a -3. So the charges. And then that's kind of related to the next one. Pretty good on your crisscrossing, where you have an ionic compound, okay, and you got to, and this time maybe I'm having you do the name too. But like, for instance, I'll just tell you potassium and sulfur. So potassium and sulfur, let's do that one. If I say potassium, and I can never spell potassium, and sulfur, okay, I want to make a compound out of that. I want to make an ionic compound. So potassium is one of the ones you're going to need to know. What's the symbol for potassium?
K.
It is K, yep. And what's the symbol for sulfur?
S.
It is S. So that's kind of where you start. And then you find potassium on the periodic table, and you'll find it in 1A, and you have a +1 up there. So actually that's going to be the charge. And then you'll find sulfur in 6A, and you'll have a -2 up there. And so it forms a -2. So this is kind of how you're going to work these. And then we're ready to crisscross. Okay, now the thing about crisscrossing is they're always going to end up as subscripts. Okay, and the charge won't be there. So if I go ahead and write K, notice that I'm going to need 2 Ks. So I'll put a little subscript 2 there. And I'll put an S for sulfur, and I'm only going to need 1 sulfur. So I'll put a 1 there. And the name of this would be potassium, what's the last name?
Sulfide.
Sulfide, exactly. Potassium sulfide. Perfect. Okay, so that's that one. The next one was basically in a solution. There's the solvent, and if I did a beaker right here, and the stuff that's a lot in amount, that's the solvent. So I'm just going to put lots, okay? That's basically the thing that you're dissolving your solute into. And then a solute is a small amount. Small AMT for amount.
So that would be like little salt particles.
Yes, solute would be the little salt particles. Yep. And I'm going to add a page for the next one. Solubility. Okay. I'll go ahead. Under solubility, that's just the amount, AMT for amount of solute, so that's there in the lesser amount, that will dissolve. So, I mean, I don't know what it is, but it seems like salt, like table salt and sugar, they have different solubilities in water. You're like, oh, it seems like it'd be similar, but you could do a little test, like get 100 grams of each. Will they both go dissolve in 100 milliliters of water? That's what solubility is. And the next one, let's see, maybe I have room down here. Yay, okay. To me, these lend themselves to a picture. So I'm going to draw, I talked about making Kool-Aid, okay? So this isn't Kool-Aid, but this is just supposed to be sugar water, okay? So basically I have water, and I'm adding sugar to both of them. I'm adding sugar to both of them, okay? Now, if all of the sugar dissolves, we call that solution unsaturated. Okay, it all dissolves, then that is unsaturated. If I add sugar to the point where, and I usually call it sludge, if I add sugar to the point where there's actually some solid down there, that basically means I've added more sugar than will dissolve. Okay, and so this is actually saturated. If somebody, like if you take a class and if you just get saturated with material, that means you're like, I cannot take another bit of material. I'm totally done. Okay, so if a solution is saturated, it means it cannot have any more solid dissolve. All right? Cool. Next. Okay. So do you remember when we had, we talked about an atom? I just think it's so cool that what we take for granted, like you guys are really good about the whole nucleus and electrons, but we didn't always know that. Okay, so actually it was Dalton that kind of kicked off the whole idea of what we know about an atom. So that will get you down the road to answer that. So Dalton was the first guy in the modern time to actually understand the concept or revisit the concept of an atom. So I'm going to say first. He was the first in modern time. First for an atom. Okay. So metals and nonmetals, I'm going to say JAG. Look for the JAG. Okay, so your periodic table tomorrow is going to be that black and white one. You'll kind of see the black JAG, okay? And remember that, so if this is my periodic table and here's my JAG, what's over here on the left? They are the metals, yes. And then right here are the nonmetals, yep. And then the next one, calculate the mass of a unit. Okay, I'm just going to say use periodic table. Use periodic table and add. And add. ADD. Okay, but here's the deal. Show your work. Show your work here. Okay, I think it's going to be worth 3 points, and if you just like use your calculator and get the right answer, then I don't know, probably take off 1 or 3 points. And you want that third point. Show your work, and I'm going to say units. And units. Do you guys remember what units would you use for how much a molecule weighs? Not grams, not pounds. AMUs, exactly. Units are going to be in AMUs. Yep. And the symbol for AMU is just a U. But if you put AMU, that would be fine too. And I did go ahead on that last section. There's like there's the formula for 3 compounds. And you need to tell me if those compounds are ionic compounds or molecular compounds. And remember when they did this, I'm just going to put it this way. I'm going to say if it has a metal equals ionic compound. If it has a metal, equals ionic compound. That's it. Electronegativity is kind of that tug of war for electrons. Okay, so electronegativity is tendency to hoard electrons. Tendency to hoard. I just like the word hoard. Electrons. Symbol for electrons, of course, E with a negative sign. Tendency to hoard electrons. The symbol for electronegativity, I don't think you need to know this, but is that kind of funky looking X with a fancy kind of pre-tail. That's electronegativity. Now with regard to trend, and this is important in chemistry, but electronegativity actually increases across the period. So these arrows are showing increasing electronegativity. So it increases from left to right. So I'll put electronegativity increases across the period. And electronegativity increases as you go from the bottom of the group up. Electronegativity increases from the bottom of the group up. Formation of an ionic compound, transfer of electrons. Let's see. Well, just to kind of remind you how that works, let's pick on the table salt. And this is the example that we did in class. So table salt, of course, is NaCl. Okay, and the way it works is actually Na, sodium metal, actually will lose an electron. So I'm going to show it going over to the chlorine. 1 electron going from the sodium to the chlorine, and then it ends up, the sodium ends up as a +1, and the chlorine ends up as a -1. So transfer of electrons form this ionic bond in an ionic compound. Formulas and names of ionic compounds, I think that's pretty fresh in your mind. I gave you the answer key for the whole crisscross. Write the formula and then give it a name. We did an example here just a minute ago. All right, last one. Now this was a term I wished I had put on there. So when you balance equations like you guys did, good job. When you balance equations, and I've got 3 equations to balance, and they're going to each be worth 1 point apiece. So when you balance them, that number that you put there, it's called a stoichiometric coefficient. And actually that's on your test. So I'm going to add that up here. Stoichiometric. If you just put stoic, but it's stoichiometric, and then coefficient. Okay, and they are used to balance your reaction. And I usually say they are the big number to the left in balanced equation. Kind of got ahead of myself though. That thing up there at the top, there actually is a question that you need to be able to know that basically, I'll just put R for reactant, arrow sign, P for product. When we see a chemical reaction written using an equation like that, it reads reactants, goes to form products. Cool. And then just be able to balance equations. And I tried to pick ones that weren't too terrible. I mean, I have to scratch my head on some of those that you guys did. And I did assign extra credit if you did all of them. So endothermic and exothermic reactions. So endothermic means energy needs to go in. Okay, endo in. So under endothermic, I'm just going to say requires energy. Requires E for energy. And actually, if it requires energy, if you're holding something that's endothermic, it's going to get cold. Okay. And then exothermic, I'm going to say energy released. E released. So there, if you're holding something, your hand's going to get hot. Activation energy, you guys did a homework that I handed back where basically, if this is an energy diagram, let's make it exothermic. So you start here, this is your R for reactants. It goes up, and then it goes down. Okay, we'll put this P for your products. And the activation energy actually is this little hump right here. Let's see, what would I say? It's a barrier. I'll just put E for energy barrier for reaction. For reaction, RXN for reaction. So that is your activation energy. It's kind of cool. And then we didn't talk about this in class, but I went ahead and I think there's only 2 multiple choice questions about pH. Because I thought the pH lab was a good one. So remember, I'll put it down here, your pH scale goes from 1 to 14. And remember, this is acidic over here, and this is basic here. Okay, so what's neutral? 7, very good. You got it. Then Avogadro's number is the one you used for your homework. That's 6.022 times 10 raised to the 23rd power. And I can see now, though, I don't have, I say Avogadro's number, but on my review sheet I don't say anything about a mole. And so Avogadro's number, mole, okay, they should actually both be on there. So we said that significance of Avogadro's number, 6.022 times 10 to the 23rd, of anything, I'll just put anything, is equal to 1 mole of that thing. So, yeah. Now, I'll go ahead and add this because I told you, like I told you, it did make it to the test in the form of extra credit. Okay, so there is an extra credit molar mass problem. I'll just put EC for extra credit, and that's kind of what you guys did with that was on the board. Okay. But yeah, they're for like 6 points, like 3 and 3. So hey, what the heck? And you do have 2 hours to take it. So, but any questions? Yay, dabbling in chemistry.